So welcome everyone to 60 Minutes in Space. Those of you who are joining us virtually throughout the program, please put your questions or comments in the chat and I'll be keeping an eye on that. We also have an audience here at the museum in the Ricketson Auditorium. Please put your question. I know you have a mechanism there to put questions and comments on little cards, and then we have a complicated system. It's not complicated, but I will get those as well so we can make sure that those questions get shared at the end with our astronomer. And with no further ado, I would like to welcome you all officially to 60 Minutes in Space and introduce Dr. Ka-Chun Yu, our Curator of Space Sciences here at Denver Museum of Nature and Science. Welcome, Ka-Chun.
All right, thank you very much, Mitch, and welcome everyone, both at home and at the museum. And what I'm going to do now is I'm going to share my screen just so make sure that we have our presentation showing. Okay, so first of all, again, welcome to our June 60 Minutes in Space. And what we do each month is talk about some of the latest news that has come out in astronomy and the space sciences. And as an astronomer, I like to talk about things from the edge of our solar system out to the edge of the universe. And so oftentimes that involves lots of galaxies. And so hence I'm showing this wonderful image taken from the Hubble Space Telescope of a galaxy cluster called Abell 1351. And this is something that is up in the sky even tonight. And so let's show you where it is. You might recognize this constellation or part of a constellation. You can see the bright stars that are outlined, and you might guess what that constellation is. It's well, it's as many of you have already guessed, it's the Great Dipper, which is part of Ursa Major, the Big Bear. And so the that purple check mark or crosshairs shows you the location of this cluster of galaxies. And so when we look in this part of the sky, we're actually looking out of our own Milky Way galaxy, away from the plane where most of the stars in the Milky Way are, and looking deep into extragalactic space. And if we zoom in to a tiny, tiny patch of sky where those crosshairs are, this is what that patch of sky looks like through what used to be the world's most powerful telescope taken at Mount Palomar in California. And so you see a bunch of kind of fuzzy looking blobs or dots in this image. This was actually taken with a camera with photographic plates. So this isn't technology that's used in modern telescopes anymore. But when we look at this with the Hubble Space Telescope, the view with Hubble is actually of this inner region that you see here. And if we zoom in, so you see some of those blobs again. And now I'm going to fade in the image that we saw earlier. So you can see that these blobs correspond to these bright galaxies in this cluster. And when we look out into our universe, we find that the universe is not just filled with galaxies, and each galaxy can have hundreds of billions of stars, but the galaxies tend to be clustered or they're grouped together. And so our own Milky Way galaxy is in a group called the local group, and it's actually a pretty small group of galaxies, but there are galaxies that are in groups of thousands of galaxies, all bound gravitationally together. And so these galaxies are all orbiting one another due to their mutual gravity. And you can see galaxies of lots of different shapes and sizes. There are spiral galaxies, there are what we call elliptical galaxies that look sort of like blobs. And here is one spiral galaxy, there's another, and another. You can see the spiral arms. And in the very center is a big elliptical galaxy. There's also another elliptical galaxy off to the upper right. And if we zoom in, again, we can see that big elliptical galaxy towards the center, and it's surrounded by spirals. The spirals obviously have the spiral-looking arms, but a lot of the galaxies that look kind of edge-on are also spiral. So like the ones off to the top here And the one kind of the cigar shape thing, we're actually seeing the spiral galaxy edge on just above that other spiral galaxy that we're looking at face on. And what's really amazing when you examine these images, and this is something that you can do at home if you search for Hubble Space Telescope images of galaxies and galaxy clusters, and you find an image of a cluster, if you zoom in on your computer and you look at the faintest blobs or faintest specks, every single splotch here is actually a more distant galaxy. So we're in these images, we're not really seeing any stars in our own galaxy. There are a handful, and you can actually, if you know what to look for, you can identify these stars pretty well. But every single very faint blob in this picture is a very distant galaxy. And the reason why they're so faint is they're even further away than the cluster that we're seeing. And so this shows you that our universe is just filled with galaxies. And then the other really remarkable thing about this picture is you see this weird looking arc that shows up. And it looks like it's bridging two galaxies. And that's actually kind of an optical illusion in the sense that that arc actually doesn't have anything to do with those two galaxies. It just turns out that you have two foreground galaxies in the same direction as that arc. And so it appears as if they're connected by the arc. But that arc is actually of a even more distant galaxy. So it's actually much, much further away than the galaxies that we see in this cluster. And if we look, and you can actually see not only is there one arc over here, there's also what looks like sort of an arc over here as well. And if we look in the lower left corner, you can see even more arcs. And you can see that these arcs have some are bluish, some are reddish or orangish. And these arcs are actually distorted images of background galaxies. And what happens is the gravity of all the galaxies in this cluster, along with the hot gas that has been expelled from these galaxies, and this gas sort of permeates this cluster. We can't see the gas in visual wavelengths, but we can observe the hot gas in X-rays. But all the gas in the galaxies, the stars, the clouds of dust in these galaxies, they all contain a huge amount of mass. And that matter can actually distort and create a lensing effect where background light from galaxies that are even further away become distorted. And so these arcs that you're seeing are due to the gravitational lensing due to this foreground cluster of galaxies distorting the light from more distant galaxies. And so one way that astronomers can use to study even more distant galaxies, so this one galaxy is probably at least twice the distance of the foreground cluster, and normally it would be very faint and it would be very hard to observe and to study, but because it's being magnified and its shape is being altered by this lensing effect, it's actually somewhat easier for us to detect. So this image shows you not only how matter is collected in our universe into not only galaxies, but clusters of galaxies, but it shows some of the bizarre sort of physical phenomena that can occur with gravity and how it bends light. All right, so with that, let's jump to our next story. So this is an image that was released by the Hubble Space Telescope folks this month. And I'm going to jump to another story that also relates to galaxies. And this is called the 3D Dash survey. And I'll talk in just a few minutes about what the survey means or what it's about. But it's basically a new survey that was released. This is done with the Hubble Space Telescope again. And this mosaic just shows you just a bunch of the galaxies that were found in the survey. And again, you see a wide variety of galaxies, lots of spirals. You have spirals seen on edge, like this one towards the right here. And then you also see lots of distant galaxies, these smaller pairs we actually see a lot of galaxies interacting. So whenever you see pairs or triplets of galaxies, it's likely that they're relatively close together and they could be gravitationally interacting. And that's another way that galaxies can influence each other, is not only can they clump together in these clusters, but they can have close flybys, and those flybys can actually distort the shapes of individual galaxies. Like this one, this looks like a spiral, but you can tell that its shape looks a little distorted, and that could be because there appear to be two smaller galaxies that could be gravitationally interacting with it. All right, so before we go deeper into this 3D DASH survey, let's talk about just the different surveys that the Hubble Space Telescope has performed over the last 30 years that it's been up in orbit. And one of the more famous ones that you might have heard about took place in 1995, and this was the Hubble Deep Field. And this is when Hubble basically looked or stared at one spot in the sky, which people thought was empty. It was devoid of galaxies, and it spent literally hundreds of orbits looking at the spot and accumulating light from this position. And it was after it accumulated all the light and combined that light together, it gave you this amazing image of many tens of thousands of galaxies. And because it's staring at a very tiny spot in the sky, you can imagine what the Hubble Space Telescope is doing is it's actually looking at or sampling sort of like a pencil thin beam into the sky. And so all these galaxies lie along this pencil thin beam. The Hubble Space Telescope has looked at lots of other so-called deep fields where it stares at one part of the sky for a really long time. And so less than 10 years later, there's something called the ultra deep field that came out. There's also something called the Hubble Extreme Deep Field, and then this Hubble Legacy Field that was also released in, I believe, in the past 10 years or so. And if you ask, how big of an area of the sky is Hubble actually looking at? Well, here is the Hubble Deep Field, so that original field that came out in 1995 compared to the moon. And we often think of the moon as this big, glowing orb in the sky, but it's only about 30 arc minutes across. And so if you were to go out, I don't think you can see the moon tonight, but if you were to go out when the moon is full and you stick your hand out and try to cover the moon with a finger, you'll find that the moon takes up less than about half the width of your finger. So it's actually relatively small on the sky, even though it can look pretty big, especially on the horizon. And you can see that the Hubble Deep Field, that very first deep field, is less than about 1/10 the size of the moon. It's about 2.7 arc minutes across. And then that ultra deep field is slightly larger, so it's almost exactly 1/10 of the size of the full moon. But that legacy field that I showed right before this slide is the largest of those three. So you can see it's almost the size of the full moon. It's about 25 arc minutes. So just slightly smaller than the moon, which is 30 arc minutes across. And you can see that that legacy field has kind of a jagged shape. And that's just because the Hubble instrument that was used to observe it is actually much smaller. And what they did was they had to take lots of different pointings, basically take lots of pictures, and then they combine them together into one sort of mosaic field. And that's why it has these weird corners and edges along the sides. And that's just because it's composed of lots of individual images. And if you have a smartphone and if you ever taken a panoramic image that's larger than what your phone normally takes, that's basically the same idea. Your phone is basically taking lots of pictures and then combining them to create one big picture. All right, so here is, let's see, here is the field of the dash, the 3D dash survey that I'm going to get back to. And so you can see that this is actually much, much larger than the full moon. So it's about 6 times the area of the moon. And again, you can see kind of the jagged edges or the perimeter of that field. And that has to, again, it's due to the fact that it's composed of a bunch of different Hubble images. And this field is actually done in optical light, or light that our eyes are sensitive to. But for the paper that I'm talking about tonight, what the astronomers did for this work was they actually used Hubble and imaged this area in the infrared. And so so here is what they did, and this animation shows you all the separate images that they used to create the final mosaic. And so you can see Hubble, this animation jumping around, showing them constructing the final image using literally hundreds of different pointings. I think they used more than 1,200 individual pointings, and Hubble had to orbit the Earth about 157 times for them to get all this data. And so it's about 6 times the area of the moon, or about 1.35 degrees square in the sky. Now, normally when Hubble is used to point and take images in the sky, Hubble has to be really accurately targeted. And that means that once it's pointed, it can't deviate at all. It can't change position. It can't change the angle in the sky or where it's looking at. And there are lots of ways in which the Hubble Space Telescope can drift. And there are a couple ways in which the engineers have designed Hubble to keep it from drifting while it's targeting. And one of them is what's known as the fine guidance sensor. And what it is, it's basically a separate telescope, or actually 3 separate telescopes. There are actually 3 fine guidance sensors on the Hubble Space Telescope. And what they do is they're used to point in the same general direction in the sky that you're trying to target. And Hubble, the astronomers and engineers who run Hubble have a catalog of millions of stars in the sky. And they know the positions of these stars extremely accurately. And in any single direction, they'll use these stars to basically guide on. And so these fine guidance sensors will lock onto, let's say, about 10 or 20, about 10 of these stars. And it takes on the order of about 10 minutes, 10 to 20 minutes for it to lock on its set of targets. And once it's locked, then if there's any sort of drift, the fine guidance sensors will detect that drift, and they'll have the Hubble Space Telescope correct that drift. And so these fine guidance sensors are really important in keeping Hubble pointed. Now, there's a problem with this, if you think about it, because if it takes 10 to 20 minutes to point Hubble, actually the 20 minutes was about 10 years ago, and then typically, I think they can point Hubble within about 10 minutes. But if you look at how close Hubble orbits the Earth, here is an image showing kind of a cartoon showing the Hubble's orbit. So Hubble orbits just a few hundred miles above the Earth's surface, and it goes once around the Earth every 97 minutes, which means that if Hubble is trying to look at something that's not blocked by the Earth, it basically has about half an orbit for it to observe that target. And so that means that typically the Hubble Space Telescope can see a target and lock onto it and look at it and integrate or keep its camera on that target for less than about 50 minutes. And so that results in a problem, because if it takes you about 10 minutes for you to lock onto a guide star and to keep Hubble tracking on your target, you're going to eat into the amount of time that you can stare at your target. So there are other ways that there are other tools that helps the Hubble Space Telescope. The Hubble does have gyroscopes. So there are actually six gyroscopes, and each gyroscope is in what's known as a rate gyro assembly. And there are two of these rate gyro assemblies inside what's known as a rate sensor unit. And there are three of these rate sensor units that are on board the Hubble Space Telescope. And so these gyroscopes are another way in which we can keep Hubble pointing in the right direction. During the last repair mission for the Hubble Space Telescope, which took place in 2009, the astronauts actually replaced all six gyroscopes. And so each of these, like I said, these rate sensor units have two gyroscopes. And so they basically have one gyroscope running at any given time, and then the other one is kept as a backup. And over time, these gyroscopes have also, some of these gyroscopes have failed. And so we don't have a full complement of six gyroscopes running. But these gyroscopes are another way to help keep Hubble pointing in the same direction, but they're not as good as the fine guidance sensors. But if you were to rely just on the gyroscopes and turned off the fine guidance sensors, then that would help you keep on target, or to integrate and to stare at a target for a lot longer, just because you're not wasting that time trying to make sure that your fine guidance sensor is locked on to a guide star. And so this was what was proposed a few years ago, where they came up with a new type of observing program for Hubble, and it's called DASH. And it stands for drift and shift. So the D comes from the drift, the A from the and then the SH from shift. And the idea is you turn off the fine guidance sensors, and the next thing you do is you rely just on the gyroscopes, and there is some drifting if you rely just on the gyroscopes, but you basically take exposures with the wide field camera 3 in the infrared mode, and you have the exposures done in such a way that it avoids the drift, so that it doesn't cause a smear in the images. So there's just enough drift where it's not noticeable in your observations. And so what they here is an example of what a Hubble Space Telescope image might look like if you were to take the full exposure with the drifting, and what you see is a bunch of noise from cosmic rays and from other artifacts. But if you instead of taking one image for let's say 300 seconds or 5 minutes, instead what you do is you take 12 separate images, and each of those images requires a separate read from the detector. But each one will also drift. There will be a slight drift in between each one during the instrument reads, but you then combine them. And then what we have then is a final image where you can actually automatically remove cosmic rays and other defects, and you actually have a much nicer final image than if you had taken it without going through this dash mode. And so here is an early test of that dash mode. And what we see in this inset is the image that's uncorrected. And so you see some smearing of the objects of the galaxies in this image. And then this inset up above is where they've done that correction, where they've overlapped the images correctly. And you see it's kind of hard to tell, but if you squint and zoom in and take a really close look, you can see that the galaxies are much tighter looking. And this is an inverse image or a negative image. So the galaxies appear as black on a white background. And finally, this is a comparison of this particular dash method with an earlier image of the same region where they're using the traditional method of staring at the sky for a really long time, and then and repointing with the fine guidance sensors. And you can see that the this current method, this new method, gives you very similar sets of features, although it's not as sensitive. You can see that this other method, earlier method, we're able to see deeper, see fainter galaxies, because they weren't able to have as many exposures in the current method. But you can see that it more or less works pretty well. And so again, this is what the final mosaic looks like. They used up about 250 hours total of exposure time on the Hubble Space Telescope using this dash method. And whereas if they went with the traditional method, it would have taken over 2,000 hours of equivalent exposure time. So this is a way of doing a really quick or much faster type of exposing to create this survey image. And you might notice that there are a lot of gaps in this image, and those gaps are there on purpose. And that's just because of the way these images were taken. They can't have very bright galaxies or bright stars in the image. And so those gaps are places where they're avoiding bright objects. All right, so here is, again, that mosaic that we saw right at the beginning of the story, where, again, we're looking at some examples of many of the galaxies that were found in the survey. So this is just a tiny, tiny fraction. Remember, this is an image that's about 6 times the area of the full moon. And as we saw in that very first image of Abell 1351, if you look at just even the smallest parts of an image, at the smallest, faintest blobs, you'll see galaxies. And so you can imagine that there are probably many millions of galaxies in total throughout this image. And when we look at images like this, remember what I said earlier, that when Hubble is staring out into space, it's if it's staring at one tiny patch of the sky, you're staring at sort of like a pencil beam that extends out into the sky. And the longer that pencil, the further away you're looking, and also the further back in time you're looking. And that's just because it takes a finite amount of time for light, even traveling at 186,000 miles per second, to reach us. And so the further a galaxy is, the longer that light is taken to travel to reach us. So it's that in this particular survey, we're seeing galaxies whose light was emitted 10 billion years ago. So I think Mitch was talking about in his introduction how we could be seeing things hundreds of years ago. Well, we're not only seeing things hundreds of years ago, but we're seeing galaxies whose light was emitted 10 billion years ago. So we're seeing not only nearby galaxies that aren't very far distant in the past, but we're also seeing galaxies that are actually very far in the past. And so their shapes, their sizes are actually very different from the galaxies that we see nearby or closer to today, just because they haven't evolved to be the galaxies that we see today. Now, you can explore this image yourself. The main author of the paper about this 3D dash image has her own website. So if you go to Lamia Mola, that's the name of the astronomer. She works at I think the University of Toronto, but if you go to her lamiamola.com, at this web address, you can actually explore this image, and they have a web app, sort of like Google Maps. So if you ever use Google Maps and where you can zoom in to part of the Earth's surface, or to see your city or your hometown, you can do the same thing at this website. So you can check out all the galaxies that have been mapped in this image through this website. All right, so my last story will again be about mapping a galaxy, but it's actually going to be mapping our own Milky Way galaxy. And as many of you, if not most of you, and perhaps even all of you know, our own, in our solar system, our sun, all the planets that orbit our sun, are just make up one star, or make up one small part of our Milky Way galaxy. So we think that our Milky Way galaxy has up to 400 billion stars in orbit around it. And our sun is just one of those stars. And our Milky Way is another spiral galaxy. In fact, it's what's called a bar spiral. And if you look at the center, you can see that the very center, that kind of the orangish glow of the Milky Way has, it looks like a kind of a rectangular ovalish bar at the center. So it's not a circular clump in the center. It's actually kind of a rectangular bar. And out of that bar, you see a bunch of spiral arms coming out. Now, this is what, I label this a cartoon map. And that's because this is really just an artist's conception of what the Milky Way looks like. The underlying map is from Robert Hurt, who created the original painting for this. And overlaid on this shows, we see the location of the sun. So that's that yellow dot just above center. And then there's also a yellow circle showing you approximately the orbit of the sun around the Milky Way. So just like the planets in our solar system orbit around our sun orbits around the center of the Milky Way. And it's orbiting due to the collective gravity of all those hundreds of billions of stars. And it takes about, on the order of about 200 million years for it to go once around the Milky Way. And we think the Milky Way, like I said, we think it's a spiral galaxy and has a bunch of spiral arms. And so you can see the labels for the arms. And our sun is part of what's known as the Orion Spur, or part of the Orion Cygnus arm. And if we zoom in closer, you can see again the different parts of the Milky Way, the spiral arms, but you can see a bunch of the starlight. Excuse me. The general glow of the Milky Way come from stars that make up the Milky Way, but the spiral arms are highlighted by kind of an overdensity or brightening of the stars, but you can also see dark regions in the spiral arms. Those are molecular clouds, and those are dark, dense clouds of dust and gas. And out of these clouds, we have star formation. And so you can see bright red regions, and those are places where many thousands of stars are all being born relatively close together and roughly at the same time. And UV radiation from the hottest and brightest stars makes the hydrogen gas glow, and that's what we see those red spots along the spiral arms. And so part of the problem with trying to make a map of the Milky Way is that we live inside the Milky Way. Our sun is located inside the Milky Way. And so you can imagine, if you are looking, I mentioned Google Maps earlier, if you're looking at Google Earth or Google Map image of your hometown, here we're looking at Denver, you can obviously view it from above, and you have a pretty good idea of where everything is laid out because you're looking at it from an airplane or from a satellite view. But you can imagine if you lived inside of the city and you're down somewhere on a neighborhood street, you're surrounded by houses and trees and other things that obstruct your view around you. And so if you're trying to map and you're stuck in that one location and you're trying to map the entire city, that makes it much, much harder. And so that is basically the problem that astronomers have. We live in a galaxy where there's lots of stars all around us, but there are also lots of gas clouds and dust clouds, and those obscure our lines of sight. And so it's actually difficult for us to figure out what the shape of the Milky Way is. And so and that's another reason why I call this the cartoon map. And that's just because this is kind of based on our best guesswork and our best observations and interpretations of those observations. but we're still slowly figuring out what the actual map of the Milky Way is. And so this next story, this final story, is about how astronomers are basically improving our map of the Milky Way. And to do that, we go to a news story that came out just a couple years ago. And this was something that I actually reported on in a 60 Minutes in Space in January of 2020. And this group of astronomers from Harvard, at the Harvard Center for Astrophysics, they basically took maps of star forming regions, and using the latest data for the positions of stars, they were able to basically map out the locations of not just the dust clouds. So these blue points show you the gas and dust clouds that they looked at, but they were able to identify star forming regions that were relatively nearby. So within a few, within about 5,000 light years of our sun, of planet Earth. And so this view on the left is a top-down view of the Milky Way. So within about 5,000 light years from our sun. And what they find is that the star-forming regions, these regions in red, tend to line up. And if you look at it from the side, from one side, looking it down at, so let's say from this direction, you actually see them not only lined up in a line, but they appear to be all roughly on top of each other in that line. And if you look at it from the side, the reason why they appear all on top of one another in a vertical strip is because they're actually along this wave pattern. And so here is the side view. And so this is quite a surprise to astronomers at the time, just because before this new data that was accurately showed you how far away the stars were, there was a lot of error in the distances to the star forming regions. And so we were never able to locate these star forming regions accurately enough to show that they were located in this wave pattern. And so the question is, well, another question that you might have just looking at this, how is it that there is such a straight feature in our galaxy when we know that our galaxy has these nice spiral arms, and that the spiral arms outline where the star forming regions are, as we saw in that cartoon painting. And so that's what this new paper is about investigating the Radcliffe Wave a little bit more. And so how does this fit in a galaxy with curved spiral arms? And this is a paper that just came out. It's called this Radcliffe Wave as a gas spine of the Orion arm. And so again, it's specifically about the Orion spur, or the Orion arm of our Milky Way. And it's by some of the same people who were involved with that Radcliffe Wave paper from 2 years ago. And what they do is they, again, they're using those red star forming regions that were identified in the original Radcliffe Wave paper, as well as other star forming regions that were identified in other recent work. And they also used other more recent work where they identified the pattern of stars in our Milky Way. So these whitish and bluish blobs are the places where there are more bright stars, and the black regions in between are the regions where there are fewer bright stars. And this again comes about from very recent work. So last year there was a paper where authors used data from the Gaia satellite, and the Gaia satellite is what people have been using to really accurately determine the positions of stars. And again, this shows you how our sun is located at the center here. So right where this center crosshair is, and the red is where you have an overdensity of stars. So you can see that there are 3 sort of broad regions where you have overdensity of stars, and they correspond roughly where we think the spiral arms of our galaxy are. So these black lines are a model, an earlier model of where we think the spiral arms are. And as you can see, this earlier model doesn't quite accurately match where we know the spiral arms are based on the locations of actual stars that have been mapped. And so coming back here, we again see the star forming regions, the sun in the center, and these red regions are the star forming regions. The bluish white regions are where we see stars as mapped from the Gaia satellite. And what the authors of this paper do is they also bring in lots of other data sets. So again, I mentioned the bright stars is the kind of the bluish, whitish blobs, the red dots or the star forming regions, and then these blue circles, these cyan circles, the black borders, those are open clusters. So they are regions where the star formation has ended, but you still have kind of a loose cluster of bright stars that are all drifting apart as they orbit around the galaxy. And then these white dots are other locations of star forming regions as measured by masers. These are kind of the microwave equivalent of lasers, and astronomers can measure those very accurately as well. And then finally, in this image, they're using maps of dust in our galaxy. And the dust tends to correspond, again, to locations where dust clouds and gas clouds are where stars are formed. And so they're using lots and lots of new and relatively recent data sets to basically help constrain the location of our spiral arm, the spiral arm that our sun is passing through. And so from these different data sets, you can get an idea that, the spiral arm roughly corresponds to this region here where the open clusters are, as well as where the star formation is occurring. And then you can even see that the gas and dust clouds tend to be on one side of the spiral arm. And this is something that we see in other galaxies outside of our Milky Way as well. So you tend to have stars located to one side of the spiral arm, and the gas and dust clouds, those dark clouds, tend to be located on the other side or one edge. Now, the one question that I had earlier was, why is the Radcliffe wave so straight? And the authors point out that if you look at similar features in other galaxies, you find that you can actually see similarly straight spiral arms. So here is an image of the galaxy M74, which is a spiral galaxy taken from the Hubble Space Telescope. And what they've done is you can see the central core of the spiral galaxy, and you have these nice spiral arms that radiate out from that central core. And the gas clouds are a lot patchier. So instead of like a nice straight set of dark clouds, you can see the gas clouds are broken up, and they have spurs and filaments that come off of them. And the spiral arms are also highlighted by these bright line of stars. So you can see that the stars are bluish white, and there are also big bright open clusters. And then you also see these red splotches where star formation is taking place. And so you can see some dark gas clouds here where a red splotch of star formation up in this upper left corner. And what they've put on here is, given the scale of how big we know the galaxy is, they put in a scale bar showing the Radcliffe wave at that same scale. And then they've also marked in a box sort of one part of the spiral arm where they've noticed the spiral arm is relatively straight. And so this is a region of this galaxy that roughly corresponds to the region that we were looking at before for the Orion arm of our own Milky Way. And they're pointing out that, when we look at external galaxies that are not our own galaxy, but spiral galaxies don't tend to have perfectly curved spiral arms. If you look at just the gas clouds, or if you look at just the star forming regions that are outlined in the gas. They can have straight features as well. And it's not just in this galaxy. If they look at this other galaxy, M83, they also notice another spiral galaxy. So here you have a nice spiral arm, or actually multiple spiral arms coming out, but there's this one stretch of the spiral arm that's much straighter than the other stretches. And so this, again, nicely corresponds with the Radcliffe Wave. And so, so having a really straight feature like we see with the Radcliffe Wave in our own galaxy is not totally, is not inconsistent at all with the idea that you can have this wave be part of the spiral arm of our Milky Way galaxy. All right, so with that, that's the end of the presentation that I have prepared, and I'm happy to answer questions that people might have about the stories that we've covered.
All right, we have a couple questions already. So let me join you on the screen here. Okay, so first of all, are there potentially more than one black holes at the center of our galaxy? And do all galaxies have a black hole at their center?
Yeah, so it turns out that whenever we've looked, pretty much all galaxies have black holes. And in fact, if we go back to this picture, because these two galaxies are close enough to have really detailed images taken from the Hubble. Actually, I'm actually not totally sure, but I'm guessing that astronomers have determined that these galaxies have black holes, but I'm not a black hole in galaxies expert. But it turns out that for all the galaxies that we've been able to look at carefully, we found central black holes, supermassive black holes. And so I'm guessing these two galaxies have supermassive black holes as well. And by supermassive, I mean, in our galaxy, we actually have a black hole that's about 4 million times the mass of our sun at the center. And so galaxies can have black holes on the order of millions. So the largest galaxies, they can have billions of solar masses of mass inside that central black hole. And so these we have these monster black holes at the centers of galaxies. And there's still some of a question as to how these black holes got so big. So one thing that I didn't talk about earlier was about how galaxies grow and evolve over time. And that's one of the reasons that astronomers like to have big surveys like that DASH survey, where they're looking at lots of galaxies, and they're looking at galaxies as we see them at different stages of evolution at different periods of time in our universe. And that's because, we live a very short amount of time compared to how long events happen in the universe. So we can't follow a star as it evolves, and we can't follow a galaxy as it evolves, but we can take lots of instant snapshots in time of all these different events over the course of the history of the universe, of different galaxies in different stages of evolution. So if we look at enough snapshots, we can build up basically an evolutionary picture. And so when we do that, we find that even some of the earliest galaxies, or the youngest galaxies that we can observe, tend to have really big black holes. We see evidence for really big black holes in them. And so far, our theories or computer models, it's very difficult for us to build galaxies in the central black holes fast enough in order to make them that big. But the James Webb Space Telescope, which was launched last December, and we're expecting results from it in the next couple of weeks. And I think we're going to have a museum event when those results get announced. The James Webb Space Telescope will help us solve some of that puzzle, just because it'll be able to peer further back in time than what the Hubble Space Telescope, how far the Hubble can see. And so as a result, we can use the James Webb to look at these earlier stages of galaxy evolution and kind of try and figure out how these black holes grew so quickly.
And so also is it just the one black hole in our galaxy, or are there more?
Yeah, well, we think that galaxies have many millions, if not billions, of black holes, and that's just because, even today there are stars turning into black holes in galaxies all around the universe. So one way that black holes can form is if a very massive star dies in a supernova, it blows up at the end of its life, and if a star is big enough, the very center, the core of the star actually collapses inwards. And if there is enough matter left over after the explosion, that collapse will form a black hole. So we see signs of smaller we know smaller black holes exist and are being born and are formed all around the universe. And so we expect even in our Milky Way, there should be many millions of smaller mass black holes. And those black holes can grow over time to, maybe, a few, 10 solar masses, or maybe tens of solar masses, or even perhaps 100 or more solar masses. But it's actually very difficult for them to grow to be millions of solar masses, or basically impossible using, if they started out as a supernova today. So exactly how the supermassive black holes got their start very early in the universe is somewhat of a mystery. They might have gotten their start as supernovae, and maybe lots of supernova created lots of black holes, and all those black holes merged together. But right now, people aren't quite sure yet.
All right, very cool. We're getting lots of questions. So in those early photos, those early galaxy surveys, why are the different galaxies different colors?
Yeah, so let's take a look at some of those images. And so the colors from these surveys have to do with the colors that you observe in. And so, we observe in optical wavelengths, but when you look at your computer or on a TV screen or a computer monitor, the way that the imagery is generated is just using three colors. So, in computer graphics, the computer software thinks in just red, green, and blue. And the light cones in our eyes also correspond somewhat to the red, green, and blue, although it's not quite the same red, green, and blue as the red, green, and blue in TVs and computer monitors. But we have similar sensors in our eyes that look at individual colors. And so when the Hubble Space Telescope observes the sky, it actually puts in filters that blocks out all light except for the light that you want to observe. And so these filters can are somewhat narrow in the sense that they don't observe, they don't allow Hubble to observe all light at the same time, but they only observe in very narrow bands of light. So in this case, what Hubble is doing is they're observing in two bands in the near infrared. And in 1.6 microns, and I believe either in 1.2 or 1.2.2 microns. And so the two colors that you see here are in blue and in red. And so one of them is at 1.6 microns, and the other one is, I'm not sure which one the other one is in, but because it's observing only in two bands, and the infrared is not, you can't see in the infrared, but the Hubble Space Telescope and other instruments can observe in their infrared in space as well as on the ground. And so what astronomers do is they take the images from the telescope and they remap them to colors that we can see. And so those infrared colors are remapped to red and blue, which we see as sort of red and in orange here. And so anytime that you see a nice, beautiful Hubble Space Telescope image, that's usually consists of multiple colors that Hubble observes with different filters. And those filters, the light from those filters are observed individually, and then they're added together after the fact using software like Photoshop, and then for a press release. So what you see in an image on that you find on the NASA website, on the Hubble Space Telescope website, has gone through lots of processing in order to give you an image that you can actually look at with your own eyes on your computer.
Very cool. Very cool. Okay, so the Earth is orbiting the sun, and the sun is orbiting the center of the Milky Way galaxy. Are galaxies also orbiting anything?
They can be orbiting something, and let's go back to that very first image that we were looking at, which was this cluster of galaxies. And so, when you have very rich clusters, and in this case, you can tell that there are many hundreds of galaxies, if not thousands of galaxies that are in this image. But there might even be thousands of galaxies that are all gravitationally bound together. And when we talked about galaxies being bound by gravity, what that means is that a galaxy, let's say, this spiral galaxy here, this is probably the most noticeable spiral galaxy, just to the lower right of the main bright galaxy in the center. This galaxy is feeling the gravity of all the other galaxies surrounding it. And so it's basically moving in an orbit based on the collective gravity of all the other galaxies. And its orbit, and I don't know what its exact orbit is in this picture, but it could be like a big, somewhat elliptical orbit like this, or it could be an orbit like that, or it could be an orbit that goes out really far and comes back. But that's just one galaxy. If you look at another spiral galaxy, so here's a spiral galaxy off in the upper right corner near the right edge, and we're seeing it kind of edge on, so it doesn't look like the spiral, that first spiral galaxy. It looks more like a flat dinner plate or a pizza that's flattened. But this galaxy is also feeling the gravity from all the other galaxies, including this one, the first one that we're looking at. So it has a slightly different orbit, given the gravity that it feels and the velocity that it has. And basically, all these galaxies are all moving in their own individual orbits due to the gravity of all the other galaxies. And galaxies tend to be much closer together than stars inside a galaxy. So in our own galaxy, and in probably all these other galaxies, it's very rare for a star to encounter another star close enough in its orbit around the galaxy where it will gravitationally have a close encounter, meaning a close encounter enough where, solar system planets can get tidally ejected or have, other things disturb the star and the planetary systems that are close in. But because galaxies are much more bigger extended objects and they orbit relatively close together, you can imagine, if you had a big size room, these galaxies might be the size of small saucer plates or small DVDs or CDs, all orbiting inside that big volume of a space, of a room. And so chances for collisions are actually much greater. And what happens is, since galaxies are made up of billions of stars, what can happen is they don't, when they have near passes, they can actually distort the shapes of the galaxies. And so here is one galaxy here where you can see that one corner of the galaxy is asymmetric compared to the other corner of the spiral galaxy. And that suggests that it's been distorted by the passage of a nearby passage of another galaxy. So astronomers are really interested in observing these clusters and also looking at surveys like the 3D Dash survey, where they're looking for evidence for distortions, for galaxies that look kind of warped or weird looking. And by looking at the statistics of these weirdly shaped galaxies, they can come up with how many encounters they might have in their clusters. And so that can give you ideas about how these galaxies evolve, because over time, when you have multiple passages of a galaxy with another galaxy, they can actually eventually merge and grow to become bigger galaxies. And that's how galaxies grow and evolve, is by merging with other galaxies, as well as merging with gas and dust that lie outside of the galaxy. So all these pictures, even though they're very pretty, they can actually contain a lot of information for astronomers, for them to understand how galaxies evolve over time.
Wow, neat. So what is cosmic microwave background radiation, and why is it so useful in determining the age of the universe?
Okay. Cosmic microwave background radiation is radiation that was emitted from the very beginnings of the universe, so about 400,000 years after the Big Bang. And it's basically emitted from all over the universe during a time before galaxies, before there were stars, and before there was really anything. It was just, the universe was just filled with hydrogen gas, meaning just atoms of hydrogen, which consists of a single proton with a single electron, as well as some helium gas, which is two atoms, or two protons, two neutrons, and two electrons. And then there's a smattering of some other elements, but it's basically a time before any of that gas collected into stars and collected into galaxies. And it's basically the furthest that we can look in time. And when we and the light that we see from that time, it now appears to us in microwaves. And so we can have special detectors on the ground as well as in space that can detect these microwaves. And because it's basically a gas before it has collected into stars, that gas is very smooth, meaning its density, there aren't very, the regions where certain parts of the gas are denser than others. The amount of changes in the density is very small, on the order of 1 in 100,000. But it's those very small changes in densities that will eventually grow into galaxies and galaxy clusters in the future. Because you can imagine, if there's one pocket of gas that has more atoms than another pocket of gas, its gravity will be slightly stronger than the gravity of the gas around it. And so that slightly denser region will start drawing in gas from elsewhere around it. And so over time, that dense region will just start growing larger and larger, meaning it will just grow with more mass, and it will continue to draw in gas. And so we think that it's those slight perturbations or slight changes in density in this very smooth gas that leads to the galaxy structures that we see today. And so the reason why people are interested in studying the cosmic microwave background is to look at those very subtle changes in the brightness of the cosmic microwave background, as well as other parameters that astronomers can measure. And from that, you can actually derive a lot of information from that early universe to properties of the universe today. So the cosmic microwave background turns out to be, this really amazing discovery and observational thing that we can look at and learn about different aspects of our universe.
Wow. All right. Okay, so you mentioned that gas and dust tends to be on one edge of a spiral arm of a galaxy and the stars on the other edge. Which is the leading edge?
I actually don't remember. One of the problems, again, this is kind of me not being a total expert on this, and I would have to look it up, because that should be something that I should remember. But let's come to, so part of the problem is that we think of when we look at this cartoon picture of a galaxy, or even when we look at a real galaxy, so let's look at a real galaxy as opposed to a cartoon picture. So we think of spiral arms as just carrying the gas and dust and the stars with it as the galaxy and that the stars as they orbit around the galaxy, they stay within the spiral arms. But that's actually not true. The spiral arms are actually a pattern in the spiral galaxies. And so what happens is as the stars orbit around the galaxy, they will actually pass in and out of the spiral arms. And so the spiral arms that you see in galaxies today are actually they won't necessarily stay in those spiral arms because they'll eventually move out of those spiral arms. And we can actually, if I had to make a guess, let's see, I'm not sure. I want to make a guess here, but I would guess that the stars in this galaxy would be orbiting in a more or less counterclockwise direction. Although, yeah, I'm not absolutely sure, but it definitely appears as if, I shouldn't say any more about this, but regardless of which direction they orbit, what happens is stars will be orbiting the galaxy in more or less circular orbits, but what happens is they'll pass into a spiral arm, and so they'll pass into places where there's lots of gas and dust, and where the gas and dust can actually block a lot of the starlight. And so right now, our sun is actually in between spiral arms. So it's not really in the Orion arm or the Orion Cygnus arm. It's kind of outside of it. But we can imagine that if we had lived in a time where our civilization or human species evolved during a time when the sun happened to be inside, not only inside a spiral arm, but inside a molecular cloud where the gas and dust can actually block pretty much all starlight. So you can imagine that there are aliens out there who've evolved, and when they look out into their night sky, they don't see any stars at all. They only see just the planets and moons in their own solar system. And so you can imagine that culture or that species would come up with a very different set of stories about the nighttime sky, and even their science, their astronomy might have evolved very differently because they didn't know about stars outside of the star of their own solar system.
Those poor aliens that you just imagined. I can actually help with a visual aid for this one. The question is, why are there different number of points in images from the stars from various telescopes? Hubble images have 4 and JWST has 6. I have the
and I think we can actually,
JWST image right here.
I'm going to have to go back all the way to the beginning again. And it has to do with the fact that light is both a particle and a wave. And so what happens is when you think about light as a wave, the starlight that's coming to you is coming to you in sort of like, you can imagine if you've ever been to the beach and you look at waves coming into shore, you have these waves that hit the shoreline, and you have one wave after another. And you can imagine starlight coming to our eyes or coming to a telescope, also coming in these patterns of waves. And I'm trying to see, there's actually a star right here at the bottom. So slightly to the left of center, towards the bottom of the screen, you can see a single star. If you look closely, there are other stars as well, but I think this is the brightest star. And as the person who asked the question had, this clearly looks like 4 spikes. There are 4 spikes to that star pattern. And we see 4 spikes because when the light hits the Hubble Space Telescope, it's the central mirror, but then there's also a secondary mirror that the primary mirror bounces light to. And that secondary mirror actually has 4 supports in a cross pattern that holds the secondary mirror in place. And then after the light bounces off that secondary mirror, it then bounces that light bounces through a hole in the primary mirror to the detectors. And so what's happening is that the light wave is diffracting around those supports. And that's what's creating that 4 spike pattern. And the James Webb Space Telescope has a much more complicated pattern because of not only the supports, but the shape of the outer mirror, the outer perimeter of the mirror is also not circular. And so that causes an additional pattern as well. And but the other cool thing to think about is, you might wonder, for those of you who've been on the beach, sometimes you've been on the beach on let's say the West Coast, and maybe you've been on the beach on the East Coast. And the beach on the West Coast, the waves are coming in from the west to the east. And if you've been on the East Coast, that the waves are coming in from the east to the west. Well, what happens if you're on an island like Hawaii? Which way are the waves coming in? Can anyone guess? You can post it in the chat. So we know that waves coming in to California are coming in from one direction and coming in from the other direction if you're, let's say, in North Carolina. But which way are the waves coming in if you're on Hawaii? Do they come in from one direction? Okay, well, the answer is they actually come in from all directions. So no matter which beach you're on in Hawaii, you're always going to get waves coming towards you on the beach. And that's just because that's actually another property of waves, is that even if the waves, if the ocean waves are coming from one particular direction in the ocean, when they hit the land, the waves will actually curve around the land so that when you're at the beach, regardless of which side of the island you're on, you'll see waves coming in from the ocean. And that's just a weird property of waves, and that's another aspect of diffraction, how waves bend. And so the fact that you see spikes in stars is because waves are bending around the structure of the telescopes that are being used to observe the star. So, and thanks, Mitch, for bringing up that background.
Yeah, and we had a couple months ago, we had Dr. Jessica Libby Roberts, an astronomer, who described these as the fingerprints of the telescope. So you can always figure out what telescope took an image.
Yep.
If you know what you're looking for. Well, I think we have about one more question, and I just want to mention, everyone, our next 6 Minutes in Space will be Wednesday, July 27th, and it will be live at the museum and also streamed virtually, so we hope you can join us. And so this is the question: when galaxies collide and combine, what happens to the supermassive black holes?
Well, we think the supermassive black holes also combine. And so that's one way. I mean, that's really the only way that you can get the galaxy, the supermassive black holes to grow so quickly. Because it turns out that, people often think of black holes as being these vacuum cleaners in space and they suck up everything. But it turns out that unless something is falling right towards or aimed right towards that black hole, it's not going to fall in. It's going to instead just orbit around the black hole. So it can actually be somewhat difficult for things to fall into a black hole if they just continue to orbit around it. And so one way to grow a galaxy and to grow the supermassive black hole is to have two galaxies collide, and the two supermassive black holes easily find a way. From computer simulations, you can show that they quickly merge. I mean, quickly means, maybe tens or hundreds of millions of years, but that's one way that galaxies and the black holes, their central black holes, can grow. And so the supermassive black holes, and I keep showing this picture, but one reason that I think this picture is centered on this galaxy, this elliptical galaxy, is that it's probably the most massive galaxy in that cluster. And so even though, I said earlier that all galaxies and clusters tend to orbit around each other, or orbit around all the other galaxies, oftentimes in these very rich clusters, you have one central dominant galaxy, the galaxy that has the most mass. And so even though, all the galaxies are feeling the collective gravity of all the other galaxies, this one central dominant galaxy has a slight edge as far as how much more gravity it's affecting the other galaxies. So this one central dominant is probably at the center, or maybe both of these are at the center of the gravitational potential field of this cluster. So basically, most of these galaxies are mostly affected by the mutual gravity of these central galaxies, along with all the other galaxies.
All right, excellent. Well, that's about all the time that we have tonight, everyone. Thank you so much for joining us, both virtually and also in Ricketson Auditorium. And we hope that you'll join us again and have a wonderful month until then.
Right. Thanks, everyone. Good night.